Report is rolling. It's Wednesday, October 22nd. We're going to put on universal gravitation. Then I'll just make a quick proposal like I can with you guys. I will get you guys taken quiz by the end of class today, and let's have that due on Monday. So I'll do this. Okay. Yeah, I see you guys popping on Kahoot, which is awesome. Actually, right before we start the Kahoot, let's slip in one more thing here. So that's okay. Well, I got a couple posters for you guys. So there's here's universal gravitation. You guys heard gravitational force. Proportional to each mass divided by the distance squared. Universal gravity. Okay. Now you can create an artificial effect if you don't actually have any real gravity by say spinning a wheel and you can walk around the inside. Okay. So my earlier classes I was showing sort of an actual version of this here, which is okay. Let's see, let's go inside here. Yeah, you guys see he's like leaning over, but he's not falling over, right? Because they're actually in a rotating. There it is, there it is. You can see from the outside. See that whole room is rotating. Okay? So on the inside, well, relative to everything in the room, you might not even know, right? Until you start to walk around, and then everything's all wonky. Now, since it's a relatively small room, you get some weird effects from actually the Coriolis effect is what this is. So at some point they're gonna throw a ball. Let's see if I can find the place where they throw this tennis ball. I think they do. Right here. Here we go. Right. Now, you guys know if you throw a ball, goes relatively straight. I mean, a little bit of parabola, but you guys see it, right? But this is gonna look like a curve ball, even though it's not really curving. Because here we go. And he's just explaining that. He's saying, "Well, I'm gonna throw it." Tennis ball looks like to the side, and then of course that ball just really followed a nice parabola path if you were to look at it from the top. Okay. So in that rotating room, I bet they all feel what a little bit lighter, a little bit heavier than normal, a little bit heavier than normal, something like that. Okay. And then going hand in hand with that, guys, since this is such a small room right there, the Coriolis effect is pretty noticeable. So I don't think I've shown you guys this one yet. So merry-go-round from the top. Now watch these kids pass around this ball. You guys see how the ball is just going in a straight line? Right? Because from the camera's point of view, which is maybe up on a helicopter, we are in what's called an inertial frame of reference. But those kids aren't. They're in a rotating frame of reference. So we see the ball just going in a straight line. Watch this again. Straight line, straight line. But if you're in the rotating frame of reference, you don't see that. You see it. Okay. Okay. Now the O'Neill cylinder is going to be okay to use as long as it's really, really big. If this R is like maybe several kilometers, then you can walk around here and it might be really hard to tell that there's anything marking going on. All right. All right. So a little bonus there. All right. So you guys ready for Kahoot? All right. So, did I bump somebody? Are you guys here? Oops. All right, I think I should. All right. Here we go. All right. And start. Universal gravitation. Depends on the board behind me. He's starting to get it. Newton had the original insight. Guys, what did Newton see that nobody before Newton understood? That the moon is moving, that the moon orbits the Earth, that the moon always keeps one side toward Earth, or that the force on the moon has the same nature as the force on an apple. Newton was the first person in history, at least to write it down, who understood, yeah, that last option right there. Okay. Now, guys, those other statements are true statements, but people have known for, well, as long as there have been people that, yeah, the moon is moving, orbiting the Earth, right? And that only one side of the moon ever faces Earth. People knew those, right? But Newton realized that, oh, hey, there's some gravity force pulling down on an apple, and actually, I think it's the same phenomenon pulling on the moon that's allowing for some kind of orbital motion. I got points on the board. Oh, yeah, points. Newton hypothesized that the moon what? Is falling around the Earth. It's actually attracted to Earth. Is a projectile. All the above. Yeah, those are all true. Right. And so, yeah, pretty much that. So somebody with like orbital mechanics, right? Right. And a special kind of projectile. It's not actually a parabola path. It'd be, yeah, just falling around the curvature of the Earth. Yeah, that's what an orbit is. Yeah, Isabella, Olivia, Bruce, Ella, Samuel. Newton reasoned that the gravitational attraction between the Earth and the Moon must be independent of distance, reduced by distance, the same at all distances, all the above. Yeah, reduced by distance. Okay. Because actually, the red and the yellow are saying the same thing. Okay. Because independent distance means that it doesn't matter what the distance is, the force would be the same. Well, that didn't make any sense. Okay. It doesn't make sense like the further out, the further the distance, the less the force. Here, do this. Here. He's looking at this relationship right here between this F and this R. He's saying the greater the R, the greater the distance, the less the force. More specifically, it's an inverse square relationship, isn't it? Yeah, that's what he's saying. All right, so you guys go with the blue one. I got Olivia, Ella, Samuel, Gavin, Bruce on fire. If the mass of the Earth increased with no change in radius, what would happen to your weight? Yeah, increase. And that is right here. Boing. So if you increase this M, this F also increases. That's all. That F is that'd be your weight. Force, weight. Yeah. We got Ella, Samuel, Olivia, Gavin, Bruce, still on fire. If the radius of the Earth decreased with no change in mass, so we're going to squeeze down the Earth. You're walking around on the surface of the now smaller volume Earth. How do you weigh? Yeah, you would weigh more. Does take a little bit of thinking, though. So I want to convince you guys that that's actually true. Okay. So what if you have the exact same mass or mass doesn't change? We're gonna squeeze it down, make it smaller. And you walk around on the surface. So wouldn't this R represent like the radius of the planet? Okay, something like that. Okay. Okay, so I still have this poster because we can navigate this formula to figure out how much would you weigh is what's this force. Okay. Now the everything in the numerator stays the same. Is that okay? Everything in the numerator is the same. Okay. Just this denominator down here changes. And if it's becoming smaller, yes, what happens to the overall fraction if you divide by a smaller and smaller number? The overall fraction becomes what? Bigger. Yeah. Here, watch this. Guess what's 100 divided by 50? What's that? Two. Right. But what if I make this 50 smaller? What if I make the 50 like 25? Ooh, four. That's bigger than two. You see how the force went up? Ooh, like that. It's different ways to think about it. I got Cole, Gavin, Ella, Olivia, Bruce, still on fire. Earth's mass decreased to half its original mass with no change in radius. Your weight would. Yeah, be half. So, if either one of these masses, let's say this mass gets cut in half, doesn't the whole thing become half of its original value? It's just taking that fraction multiplying by half. That's all it is. Whole fraction times half is half. Oh yeah, Samuel, Ella, Cole, Olivia, Bruce, still on fire. The gravitational force between two massive spheres is always an attraction, depends on how massive they are, depends inversely on the square of the radius between them, or square of the distance between them, all the above. Oh yeah, all the above. That's exactly what this says. Hey, this right here. Okay. G_m over r squared is the force. That's it. It's all right there. All right there. Yeah. Samuel, Cole, Ella, Olivia, Bruce. Which force is bigger? The moon attracting the Earth, or the Earth attracting the moon? Oh yeah! Everybody is getting it right. That's Newton's third law. Oh yeah, Newton's third law. Equal and opposite. Yeah. Ella, Samuel, Cole, Bruce, Olivia. Gravitational force between two objects is called 100 newtons. If the distance between them is cut in half, what's the new force? Hmm. Wow. Yeah, so it's actually four times the force, 400. Here, let me show you guys that that's true. So in my calculator, let's say all this GMM comes out to like 100 units. So 100 units there. Okay. Okay. And let's say this R is like 1. Okay, do 100 divided by 1 squared. Is that okay? Okay. So the force would be 100 units, whatever those units are, newtons, pounds, whatever. Okay. Okay. But what if I take this radius and I make it half of its original value? Now it's still being whoops. It's still being squared, but now it's half as much as it was before. Half squared. Okay. What do you guys think that's going to be when I hit enter? 400. Yeah, because 1/2 squared is 1/4, and 1 divided by a quarter is like a multiple of 4. Hey, it's all right there. Okay. If you ever saw a quiz question like this, and you weren't sure, could you just make up some numbers exactly like I just did here? Just kind of play out some numbers. You can pick any set of numbers, and proportionally, the answer is always the same. I got Spencer, Samuel, Olivia, Bruce, Cole, on fire. Force of gravity is greatest on you when you're standing at the center of the Earth, on Earth's surface, far above our surface, or all of the above. Yeah, right at the surface. Only got a couple of guys got that right. Here, I'm gonna dig through and find a poster because I'm thinking of a specific one. Where is it? Ah, here it is. Here it is. I got just the one. Just the one. So, do you guys remember this? Remember this? Yeah. So, if you're at the surface, now this is in terms of gravity field, but at the surface, isn't this 9.8 meters per second squared at the surface? It's capital R. Right. Now, if you take off a rocket and fly away, doesn't the gravity force get weaker, weaker, weaker? The field and the force would both. Right? They would both approach zero, asymptotically approach zero, wouldn't they? They less, right? At the center, guys, at the center of the planet, isn't there a zero gravity field? Because doesn't every grain of sand pull you in a different direction? It all cancels out. So if you brought a bathroom scale with you and try to stay on the scale, well, everything's just floating around. So the scale would just read zero. Right? And then as long as you have a uniform density planet, then this ends up being a linear relationship. Now, realistically, do you guys think realistically the Earth gets more dense closer to the center? It's like being compressed down. Right? So in reality, this graph doesn't look exact like this. I think this curve comes out a little bit. You guys get the idea. If it was uniform density, it's pretty much that. So the most you ever weigh is pretty much right around the surface. Got Gavin, Olivia, Spencer, on fire, Bruce, Cole. Reason the moon does not fall into Earth. The moon has less mass than Earth. The moon has sufficient large orbital speed. Gravitational pull of other planets keep the moon up. All of the above. What's the primary reason? Why doesn't the moon crash into the Earth? Sufficiently large orbital speed, right? It's moving fast enough to the side that, see, it is always attracted to the Earth, but it's moving so fast to the side that it never actually gets any closer. And that puts it in orbit, right? You guys can calculate orbital speed. You guys remember orbital speed? Like that. Yeah, so is Jupiter pulling it up? Nah, not really. Massive amount, right? Like the Earth's not falling into the moon either. The Earth is more massive than the moon, so that's why. Yeah, but orbital speed. Gavin, Olivia, Spencer, on fire. Cole, Bruce. Lunar month, about 28 days. What if the moon was closer to the Earth? How much time would it take for the moon to go around? Yeah, less than 28 days. Right. Uh, and that has everything to do with how far away it is from the Earth. You could approach this from orbital speed point of view. You could approach this from Kepler's third law point of view. Guys, how about low Earth orbit? Do you guys know? Did we go over this? I forget if we did. Maybe somebody knows anyway. Does anybody know how long it takes the International Space Station in low Earth orbit to go all the way around the Earth? Faster than that. It takes about 90 minutes. It takes about 90 minutes. And you can find that too with the equations that we're doing. Yeah. Okay, so low Earth orbit, about an hour and a half. By the time you get out to the moon, it takes 28 days. Right? Hey, do you guys think here, I'll draw this out a bit. Okay. So like here's the Earth, E for Earth. Here's low Earth orbit. So-called LOE, low Earth orbit, little satellites. Takes 90 days for that to go around. Okay. Here's the moon way out here. Moon. Okay. Takes 28 days to go all the way around. Okay. Also, it's moving slower. Right? So gravity field from Earth is weaker. It's moving slower tangentially. Got some tangential velocity v orbital. Right? Do you guys think that there's a point somewhere, maybe about here, I don't know, maybe about here, where it would take exactly 1 day to circle the Earth? Do you think there's a place where that could happen? Somewhere between 90 minutes and 28 days. I bet there's like 24 hours. Right? That's actually a special orbital location. It's called geosynchronous. So if you're on the equator and look up in the sky through your telescope and say, "Hey, there's a satellite up there," it actually tracks over the exact same location on the surface of the Earth all day, every day, all 24 hours. It just goes around. Okay? It's called geostationary, stationary relative to a particular point on the surface. Okay. Samuel, Olivia, Bruce, Spencer, on fire, Cole. Planet has half of Earth's radius, but the same mass. You would wait. Oh, you guys saw this question earlier. You guys remember it? Well, you guys saw the opposite version of this question. Oh, no. Or no. Sorry. What was this question? I'm thinking. Right. So we'll find out soon how many you guys got that right. But you guys remember you saw this question earlier. If the Earth was compressed down so that everything in the numerator stays the same, including its own mass, but its radial size gets smaller and smaller, that's what happens. What happened earlier today? We divide by smaller numbers, the overall fraction gets what? Bigger. So the answer is you'd have to weigh more. Right? Actually, you'd weigh specifically 4 times more, wouldn't you? Because 1/2 square is 1/4, 1/4, 4 times more. Yeah, that's true here. Oh, yeah, and that's exactly the answer. Yeah, 4 times. All right. Samuel, Olivia, Spencer, Bruce, Cole, on fire. Mass of Jupiter is 300 times the mass of Earth, but you would only weigh about 3 times as much on the surface as Earth. Why? Jupiter's 300 times more massive. Why would you only 3 times as much? Yeah, large radius. There you go, large radius. Right, so here, if guys, what if the radius was 10 times as much? What's 10 squared? 100. So 300 times mass divided by 100 down the bottom. Yeah, we get three times as much. Yeah. Large radial size. Samuel, Olivia, Spencer, Bruce, and Cole. Oh, what if you stood atop a ladder on Earth that was as tall as Earth's radius? How much would you weigh? That's this guy right here. Like he's standing on top of a tower that's as tall as Earth's radius is large. Right? Hasn't this guy right here effectively doubled his distance from the surface? Doubled his distance from the surface? Right? So whatever he weighs at the surface, let's see, if you double that distance, what if this equation said happen if you double this distance? What happens to the overall force? Guys, what's 2 squared? 4? What's 1/4? 1/4. And that aligns with this point right here. See, like double the radius, point, you're 1/4 of the gravity field. So 1/4 weight. Yeah, 1/4. Should be 1/4. All right. Yeah, we've got that. 1/4. Olivia, Samuel, Spencer, Bruce, Cole. Since Earth is attracted to the sun, why doesn't it fall into the sun? Ooh. Oh. Sufficient tangential velocity. Right? Same reason that the moon wasn't crashing into the Earth. That was an earlier question too. It's almost kind of a repeat question here. Right? Yeah, it's moving fast enough. Got Anna on fire. Samuel, Spencer, Bruce, Cole. 40 Newton man stands on top of a very tall ladder that's 1 Earth radius. Hey, everybody better be get this right. We just did this one. Ah. Yeah, 110 because it's 1/4 as much as before. Okay. So yeah, that's this right here. Right? Double your distance. 1/2 squared. That's like 1/4 of the original weight. Got Gavin, Fire, Anna, Spencer, Bruce, Cole. Gravitational force between two masses. It's called 40 newtons. What if each mass loses half its value? Yeah, 10 newtons. Okay, so why 10? Okay. So here's some original force, maybe 40 newtons. So that's the original. Okay. But guys, what if this m and also this m are each cut in half? Guys, what's a factor of a half times a half? Is that a quarter? Half a half is a quarter? And what's a quarter of the original 40? Maybe 10. Yeah, it's 10 newtons. Yeah. You got Gavin, Olivia, Spencer, Bruce, and Cole on fire. Gravitational force between two spheres, 20 newtons. If the distance between them is cut in half, ooh, they're getting closer together. Ooh, it's new force. Oh yeah, yeah. I bet you guys got that. So we're saying here, if you cut this distance in half, yeah, 1/2 squared is like a quarter, and it's 1/4. So it'd be 4 times as much. Like, force got to be getting stronger. They're getting close together. Yeah, so 4 times, but 4 times 20 is 80. Yeah, 4 times 20 is 80. Okay. I got Olivia, Gavin, Spencer, Bruce, Cole. Gravitational force between two spheres, 40 newtons. If each mass loses half its mass. Yeah, because half times a half be a quarter. A quarter of the original 40 is 10. Yeah, that's it. Got Samuel, Gavin, Spencer, Bruce, and Cole. Back on fire. What's that number? 10 to the negative 11. What does that look like? Oh, yeah. You guys see if you take this decimal and skid it 11 places to the right, that becomes 6.67? Okay, so it is 6.67, just off by 10 to the 11. Yeah. So universal gravity constant. Got Samuel, Gavin, Spencer, Bruce, Cole. Ooh, is that it? Oh, we got a tight race. Last question. You guys ready for the win? For the win. Who's gonna win Kahoot? 5.98 times 10 to the 24 kilograms.
That's easy.
10 to the 24. What is 10 to the 24? Oh, yeah. Everybody get it right. Uh, who recognizes that now? Guys, that's the mass of what? Earth. Yeah, that's the mass of the Earth. Yeah. Podium with the bronze. Spencer with the oh, what just happened? Go back. Where's my podium? Hey, hey, where'd you go? Oh, yeah. Oh, oh. Well, who won? Who had the goal? Oh, probably Cole, right? Yeah. All right. Well, guess the game's over. Yeah, sure. All right. Right, so let's knock out some puzzles. Do some puzzles, and then last few minutes of class, I'll get you guys to take on quiz. Right, so puzzle time. Right, so we're looking at these puzzles. Let's see. I think we had. Hmm, yeah. I think we had done some of these circular motion questions. Yeah. Okay. I think yesterday we did these two, right? The circular motion. Yeah. Now the next ones I had marked to do. That's mouse. Actually, no. We did do these, didn't we too? All right. So here, let's find a new one.
Wait, are we going against that?
Let's do number 20. Number 20. Okay, number 20 right here. Approximate the acceleration due to gravity near the surface of Mars. That's really open-ended, so I think you need some information to be able to answer something like that. Okay. So, number 20. Okay, so what information? You need 3 pieces of knowledge. What 3 pieces of knowledge do you need to answer a question like number 20?
Okay,
So find the gravity field surface of Mars. Do you know the universal gravity constant?
Yeah.
Okay. 6.67 times 10 to the negative 11 meters squared per kilogram squared. Okay. Now I'm going to open up my Google machine, get some more numbers. Good. Google. Guys, what else do we need to know about Mars?
about what?
To answer number 20, to be able to calculate number 20, we'd have to know the what and the what of Mars. Yeah. Okay. Radius of Mars. Do I want miles?
No.
Let's go meters. Look, scientific notation. So 3.39 times 10 to the 6 meters. Right, so I'll write that down. So I'm write that down. Right, so the radius of Mars is 3.39 and then 10 to the 6 meters. Okay. I think, isn't that about half of Earth's radius? Because wasn't Earth 6.38, 10 to the 6, something like that? What else do we have to know? Yeah, mass of Mars. And measured in what? Kilograms. Go kilograms. There you go. So I'm writing this on paper. Mass of Mars is 6.42. I'll call it 6.42. And that's 10 to the 23 kilograms. You guys remember Earth was 5.98 times 10 to the 24? Okay. It's what if I round both of those numbers to 6? So Earth is 10 to the 24, Mars is 10 to the 23. So you could say that Earth is approximately how many times more massive than Mars?
10.
Yeah, 10 times. Yeah, 10 times more massive. Ooh, side quest there. Got that. All right, so now gravity field. Guys, what's a good expression for gravity field?
GM over R.
Yeah, GM over R squared. So that. Okay, so if you walk around the surface, how much gravity field do you feel? Okay. No, because the fact that Mars is both smaller radial size and also a smaller mass. What do you think gravity field is going to be on Mars compared to Earth? Larger or smaller? Yeah, probably smaller. Okay, so let's see. Let's go 667, 10 negative 11. Got 642, 10 23. And then 339, 10 to the 6. And don't forget to square that. Okay. I'm going to pull out a unit here. I'll call it meters per second squared. So just to have numbers in my fraction. Okay. All right. So you guys here. Let's see if we all get the same thing. We say, can you correctly plug this in a calculator? Okay. So you know the process is you need to know some values. So we went to Google, found some values. Here's gravity force. If you divide by the mass of anything at surface, you get gravity field. Plug it in. So calculator. Let's make sure we're all getting the same correct answer. And if you're not getting the correct answer, then you're typing it wrong somehow. Right, maybe you're forgetting parentheses or something. Of course, I'm modeling it in front of you right now, so you can also see that. Okay, I think that should do it. Okay. And just double check. Should guys, if I get a number like 15, does that sound about right? 15? Yeah, you're right. That would not be right because that would be more than 9.8. Right. What if I get a number like 4? Would that be reasonable? Yeah, that would be believable. Let's see, what is this? 3.7. Yeah, I think that sounds about right. Just think about 3.7 meters per second squared. There you go. So maybe about less than half of Earth gravity. I think it makes sense. All right, you guys getting that too on your calculators? Plug in all the scientific notation and whatnot. Okay. I guess we finished with that one. We pick another one off this page. Mm. Ooh. Yeah. Ooh, I like this question, number 29. It says, imagine that there is no force of gravity somehow. Let's say we turn off gravity, and you're at the equator at sea level. Oh, they gave you the mass of, or sorry, the radius of the Earth in kilometer. Use your answer. Okay, whatever. Calculate the centripetal force needed to keep you from flying off into space due to Earth's rotation. And they're giving you a mass of 50 kilograms. Yeah, this is a pretty good one. So some critical thinking going on here. Now, you do need the mass of the Earth, so I'll give you guys that number. And you need to know something else too, but I think you guys can figure out some things. So we're going to apply some critical thinking. You guys ready to do that? Okay. And when they say the necessary centripetal force, even though there's no gravity in this made up scenario, do you think maybe what if you had like Velcro? Because what if you like glued some Velcro to the ground and got like a Velcro pad and you like, just hook it right? Like how many newtons of force could you guys imagine to keep yourself from flying off into space? Okay, so draw this out. Stop here. So get the Earth, North Pole, South Pole, equator. Okay. And the Earth is spinning west to east, so that direction right there. Okay. Now, if you were on the North Pole, then relative to the spin of the Earth, well, you'd be fine. Okay. Okay. But if you're on the surface, okay, and the Earth is spinning fast enough, let's go a little faster, a little faster, a little faster. Ooh. Even with Earth's gravity, do you think at some point you'll like fly off into space? Yeah, if the Earth was spinning too fast. Actually, what happened at that point is that everything on the surface just kind of like float off in space, and the planet would like start to break up. And everything. Okay, but all right, so let's bring this back to just regular Earth rotation. Okay. So I think we're gonna have to know some things, want to find some things. Okay. All right, so you're allowed to know G is 6.67 times 10 to the negative 11 meters per kilogram squared. That might be important. I don't know. We're going to find out. They did tell you the radius of the Earth. I'll put it in meters. 6.38 million meters. Do you guys think that? Oh, I know why they didn't say the mass of the Earth because that's actually not. Right. Well, I'll list it here anyway because I might have some follow-up questions where that might be relevant. 5.98 10 to the 24 kilograms. Okay. This here. Your own mass, they're telling you, is 50 kilograms. Uh, how about guys? How about this omega here? I think we do have to have a numerical value for this angular velocity. Isn't that what omega is? Angular velocity. That's to say, how fast is the Earth rotating? Right? You can tell me at least one way to quantify how fast is the Earth spinning on its own axis. One what per what?
For one.
Yeah. Yeah, one revolution every day. Yeah. Yeah. So I can say omega is one rotation. I'll say rev for revolution every one day. That would be true, wouldn't it? Yeah. Now, let's have some railroad tracks because the number one for omega doesn't work well in the calculator, right? Unless I change the units to what per what? Radians per second. Aha. Okay. So how many radians per second is this? Can you guys imagine the Earth is very slowly spinning? It takes 24 hours to go all the way around. Okay. How many radians per second? Well, how can I convert? Guys, how many radians in a revolution? 2 pi. Yeah. There's 2 pi radians is equal to 1 revolution. So now I got radians per day. 2 pi radians per day. Huh. I gotta get some about seconds. So, could you go from days to hours and then work a change of time down there? Okay. How many hours in a day? 24. 1 hour is how many minutes? 60. And 1 minute is 6 seconds. Okay. Now the only units I have left on the board are radians and seconds. It'd be radians per second. That's it. And to get a numerical value, I'll just pop this in the calculator. So I got 2 pi. Actually, that's all I have in the numerator. So divide by, and then open parenthesis. And down here, we got a 24 and a 60 and another 60. Yeah, this number looks right. So that is 0.0000727 radians per second. That's a tiny number. Can I write that in scientific notation? Might be easier to work with that way from here on out. How many? How would you write this in scientific notation?
7.27 times 10 to the power of 5.
Yeah, 7.7, 10 to the minus 5. Yeah, and then radians per second. Of course, yes, the same. Okay, so now we know how fast the Earth is spinning. So what's the required force that, even if there was no gravity, like what would be the strength of your Velcro connection? Maybe you have Velcro on your shoes to prevent you from floating off into space. Right? Can you guys think of a way to do that? That maybe involves this omega here. Remember this? Remember this? So the question that we're trying to talk right now says, what is the necessary centripetal force to hold your 50 kilogram mass on a planet of some radius? And we just found how fast it's spinning, which is relevant too. I think it's right here. I think this will answer it. You guys think this will do it? Okay. All right, let's do that. So let's go. The necessary centripetal force is m omega squared r. So your mass, 50 kilograms. The angular velocity, 7.27, 10 to the minus 5. That's radians per second. Don't forget to square that. Ooh, should make it really tiny. This guy's 10 to the minus 5 squared. Now it's like 10 to the minus 10. Ooh, that's really tiny. But the radius of Earth, no, that's pretty big. So 6.38, 10 to the 6. 10 to the 6, that's a million. Ooh, that's meters. Are you guys okay with that so far? Like following the logic of where I'm getting all these individual parts from? Okay. All right, so last step is, can you correctly plug that into this calculator? So I'll model it for you guys right here. You guys are also plugging into your calculator. The same thing. So got this. Got that. And that. Okay. Now, I think I did correctly plug everything in. Okay. But how can I know for sure when I hit enter? Okay. So, like, what would be a reasonable value? Hey guys, if you have a mass of 50 kilograms, let's think big picture here. How much do you weigh on there? How much do you weigh about? Yeah, like 500 newtons, right? Right, to go from kilograms to newtons, you multiply by 10 meters per second squared on Earth. Okay. So I know you weigh 500 newtons. Okay. Now, as a 500 newton person, actually, really anything at the surface of Earth, because is anything at the surface of Earth in any danger, realistically, of flying off the surface? Not at all. In fact, it's really hard to get into space. Right? It takes a lot of energy to get into space. Right? So, compared to a 500 newton weight person, how many of those newtons do you think are really required to keep that person on the ground from spinning off into space? What sounds reasonable? 5,000? Does that sound reasonable? No. How about 50? It's probably even a little too big. How about five? I'm going to guess maybe approximately five, somewhere in there. How about 0.005? That's probably too small. So maybe in the ballpark of about five, I could believe. Let's see. Oh, 1.686. I'll round it to 1.7 newtons. Yeah, I can believe that. That looks reasonable. Is that pretty close to 2 newtons? Guys, that's this right here. Guys, 200 grams weighs 2 newtons. That's pretty close to this. Right? So this is how much weight is actually required to keep you on the surface of the Earth from flying off into space. Not very much. And there's another way you can frame that too. Is if you're on the equator and you're standing on a scale, and Earth is actually pulling you down with truly 500 newtons of weight. I'll say mg equals 500 newtons. But remember, on the equator, you're actually moving on a curved path.
Mr. Griffin, what number is this?
What number is this? 29? Yeah, 29. Yeah, thanks. 29. I got a follow-up question for you guys. This 500 Newton person standing on a scale on the equator as the Earth is rotating, just ignore me. The scale doesn't actually read 500 Newtons. How much does that scale actually read? I want somebody to figure this out. Well, somebody get it before I walk around the classroom? Yeah. Oh, yeah, right. How much does that scale right there actually read? Who's gonna figure it out? Who's gonna figure it out? Somebody gonna figure this out. The first. That's my physics song.
Wait, what's your gonna give a take home quiz?
Oh, yeah. Right. I'll give you guys a little more. I'll give you a chance to take home quiz while you guys are thinking about that. What does that scale actually read?
In Newton?
Yeah, it would be newtons, right?
850.
No, it's not that much.
What time is that?
See if anybody can get this before I hand out all these take-home quizzes. Oh yeah.
What was it?
Awesome.
500
Take that race. Who's gonna figure out what the scale reads? What does the scale read?
I don't know if they can this.
Any last guesses? Any last guesses? I think the scale reads 498.3 newtons. Why do I think it's that? Exactly. Guys, it's the difference between these two right here. Right? So this guy is actually being pulled down with 500 newtons of force. The scale only pushes up with a couple of newtons less than that. There is a net force on the sky. What's the net force? 1.7 newtons, which acts as a centripetal force. That's what's keeping him moving on a curved path on the equator. You see it? Okay. Now, if this guy was standing on a scale at the North Pole, the scale reads 500 newtons. He goes to the equator, the scale then reads 498.3. Okay. A little bit less. Let's see. Well, there's a lot of other fun questions here, but I think we'll have to save some of these for another day because we got just a short time left. All right, so we'll wrap that up right there.